Hello, my dear friends. Welcome back to the online lecture video series on electromagnetic theory by areas people. In the previous module, we have discussed about the gradient of a scalar field. In the current module, we will discuss divergence of a vector field. Gradient of a scalar field was an operation which gave you a vector field in response to a scalar field. The divergence of a vector field will give you a scalar field in response to a vector field. The divergence of a vector field means the net outward flow from a unit volume centered at a given point. That is, if you have a point P here, a unit volume which is enclosed in the given point, how much flow would be there for a given vector from this volume is given to us by. You may remember while discussing the surface integrals, I told you that the surface integrals can be used to calculate outward or inward flow. In this module, we would see how. But before we do that, we should observe the changes between normal to an open surface and normal to a closed surface. If you have an open surface, it can have normal in two different possible directions. If you consider this to be the surface, you see the definition of a normal says if you draw any vector in a plane, then the normal is the vector which would be perpendicular to all possible vectors on the plane. See, you may draw many vectors on this plane in whatever direction you may like. Now, you should be able to identify a vector which can be perpendicular to all possible vectors on this plane. So the obvious answer would be a vector which is directed either upward or downward. Now, what of them is the correct answer? The answer for that question is both of them are the correct answer. That is, the normal can have both the directions. A vector which is going upward is also the normal to the surface. A vector which is going downward is also normal to the surface. But if this surface is somehow part of a closed surface, then that may not be the case. When it is a part of a closed surface, it can have only one possible direction for a normal, and that would be pointing away from the volume enclosed by the closed surface. I would also take this opportunity to explain the difference between an open surface and a closed surface. Consider this diagram which I have shown you. This is the diagram of a cuboid. Now, if somebody asks you what is the volume of the cuboid, it would be very easy and straightforward, LBH. But if I ask you what is volume, then volume is the space enclosed by this closed surface. See, if by some case this part is not present, then the surface would be remaining an open surface. It would not become a closed surface. For you to understand, imagine you have a water bottle. If this water bottle is closed, then the surface becomes closed. If this water bottle is not closed, if it is open, then the surface is open. Again, when it is closed, you can hold fluid inside it in all possible directions. But when it is open, you cannot hold fluid inside it. See, if the body has the ability to hold something inside it, to enclose something inside it, then that body is a closed surface. If not so, it is an open surface. Now, when this surface, let us consider the same surface which we have seen earlier. See, this is pretty much similar. Only difference between the earlier scenario and the current scenario is now that surface, this surface here, is part of a closed surface. In such case, you cannot answer that this also has possibility of becoming a normal to this surface. No. In that scenario, only possible normal would be this, because normal should always be pointing away from the point. In this lecture, we would also see what are the normals for 6 different surfaces of this cuboid, because you know cuboid has 6 faces, each face is a surface, so each surface will have its normal. We will see what are the normals for these 6 different surfaces. See, these are the 6 surfaces of a cuboid. I try to illustrate to my best here. There are 2 surfaces which are colored black. This is the top surface and this is the bottom surface. See, by the principles of coordinate geometry, you can say that this is a z is equals to constant plane. This is also z equals to constant plane. This is k1, this is k2 for that matter. But at all points on the surface, z is constant. So how is this area formed? This area is formed because of variations in x and y. So the area of this sheet is dx dy. Similar to this, because these two are parallel, they have same area in magnitude. But the difference comes in the direction of the normal. Normal to this surface is pointing upward along az cap, whereas normal to this is pointing downward along minus az cap. So the normal of the top surface is dx dy az cap, whereas normal to the bottom surface is minus dx dy az cap. I hope you can enjoy the difference between the top surface and the bottom surface. Similarly, I have colored 2 surfaces in green. Our convention knowledge is that this is x-axis, upward is z-axis, and going into the screen is ay cap, y-axis. So if something is going outside, that is minus ay cap. Fine. Now you see this, it is along ax cap, because this is going from left to right, whereas this is along minus ax cap. Normal to this surface is along ax cap, and for this is minus ax cap. What about the area? See again, these two surfaces have same area and magnitude because they are formed by varying by a. So normal to the right surface is dy dz ax cap, and normal to the left surface is minus dy dz ax cap. You should understand my limitation here. I tried my best to show you a three-dimensional figure in a two-dimensional screen, but there are some limitations. You may see there are two surfaces which are not possible for me to show you. I have left them uncolored because if I color one top front surface, I could not show you the other surfaces because that then opacity comes into picture and I will not be able to show you the left surface or the right surface. So I have left two surfaces uncolored. One is the front surface and the other is the back surface. So the normal to the front surface is obviously coming out of the screen, whereas normal to the back surface is going into the screen. That is, normal to the back surface is along ay cap and normal to the front surface is along minus ay cap. What about the area? They are formed by varying dx and dz. So the area vector for the front surface is minus dx dz ay cap and area vector for the back surface is dx dz ay cap. Those are 6 different differential surface elements of a cuboid. Let us revisit the concepts of a surface integral. The general form of a surface integral would be looking like this. In this, S stands for the surface over which we are considering the integration. V bar is the vector field in which is being integrated. ds bar is normal to the surface at any given point. Now, what happens if a surface is not just a single surface, that is, if the body is not just a single plane surface, but if it is combination of different surfaces? Then how would this turn to? For example, consider that you have one surface and you have another surface. This is along ax cap and this is along minus ay. Now, how to integrate this over this total surface? The answer would be, I would be first integrating along S1 V1 bar dot ds1 bar, where V1 bar is the value of this vector field at the center of the surface. ds1 bar is the normal to the S1 at individual points of the surface, plus this is S2 integration over S2 for vector field 2 bar. This is again same. I am integrating over the second surface, and the vector field will change, as the vector field by definition is a vector whose direction and magnitude change with the space. Again, ds2 bar is normal to the second surface at given point. So this is how a surface integral would look like. That is what we have discussed. It is the integral sum of the algebraic sum of individual surface integrals. Now, what is a closed surface integral? The difference between a closed surface integral and open surface integral is just that A closed surface has ability to hold volume inside it, whereas an open surface can't. That is the only difference between a closed surface integral and an open surface integral. So when a closed surface integral, it also has different surfaces. So a closed surface integral would mean sum of those different surface integrals. To illustrate my point, let us consider the cuboid which we have seen. So the closed surface integral v bar dot ds bar over a cuboid will be equal to 6 different surface integrals, sum of 6 different surfaces. You may also note that the vector fields are also changing for different surfaces. And not just the vector fields, the normals also change. So this is the closed surface integral. What is the intuition from it? I have already told you that for a closed surface integral, the normals would always be pointing outward. Now, if the normal is always pointing outward and you are calculating the components along normal, that means you are trying to determine the outward flow of the vector field from the cuboid. Because closed surface integral gives the net outward flow from it. I hope you understand what I meant by it. Let me repeat it again. In a closed surface integral, what we are doing is we are adding 6 different open surface integrals where normal to each surface is pointing away from the volume. Using the dot product, we are finding the component of this vector along this. We are finding the component of this vector along this. We are finding the component of this vector along this. And all of them are pointing away from the volume. That means we are trying to determine how much of the vector field would be flowing away from the volume. So the technical term for this is net outward flow from a body. So a closed surface integral gives us net outward flow from a body. Right? Let us look back at the divergence, definition of the divergence. Divergence is net outward flow per unit volume, whereas the closed surface integral gives us the net outward flow for a given volume. So to determine net outward flow per unit volume, we simply divide the net outward flow for a given volume with the volume given. This is quite obvious. If I know the cost of 10 pence, I can calculate cost of 1 pen. It is represented as del dot V bar, where del operator is in coordinate system, in Cartesian coordinate system, it would be, okay, let me derive that expression for Cartesian coordinate system and I'll tell you the expression later. Expression, I'd like to determine the expression of divergence on a vector field in Cartesian coordinate system, 3-dimensional Cartesian coordinate. To determine this, we have some requirements. We have a numerator requirement and we have a denominator requirement. Denominator requirement is that we need to find the volume, and numerator requirement is we need to find the closed surface integral. To determine closed surface integral, we should have a standard closed surface defined. And in case of Cartesian coordinate system, that standard closed surface is a cuboid of dimensions dx, dy and dz. Now, we need to find the closed surface integral. For that, we need the differential elements of 6 different surfaces that we have already seen, and the ranges or the limits of integration for 6 different integrals. How do we get those limits? We will get those limits by analyzing the shape of the coordinate system, the shape of the cuboid according to the Cartesian coordinate system. In addition to that, you may remember that at each integral, the vector field has different values. We need to determine those different expressions. We do that using principles of differential calculus. So let us look at the first step, the standard closed surface. The standard closed surface is a cuboid of dimensions dx, dy and dz. So from that, using the principle of LBH, the volume of the cuboid is dx, dy, dz. So the denominator part is ready with us. We have to find the numerator part. To find the numerator part, we need the differential surface elements, which we already have. You might have seen. We will again go back there. But we need to obtain the limits. How do we obtain the limits? To do that, we use the principles of coordinate. Let us look at the coordinate geometry of the cuboid. Let us assume that the center of the cuboid is at xc, yc and zc. Then, you know, there are 6 different surfaces, or some may call it 6 different faces. Now, at these 6 different faces, at any instant, one of them would be constant and the other 2 would be varying. We have to find at what surface which variable out of x, y, z is constant and which of them are varying. If they are varying, from where do they start and from where to where they end. Let us observe this for a top face and a bottom face. Now, this is the shape of the coordinate geometry, right? The Cartesian coordinate system. This is ax cap, this is ay cap, and this is az cap. This is the cuboid which we have considered, our standard cuboid, where the center value is xc, yc, and zc. Now, let us determine the centers of top surface and the bottom surface. So, if you draw a vector from top surface to bottom surface, right, this is vector 1 and this is vector 2. Let me call this as vector p and let me call this as vector o. Now, this vector is along az cap, whereas this vector is along minus. Now, you may remember that a bar can be written as mod a cap. Any vector a bar can be written as mod a cap. For both these vectors, we have unit vectors. For once it is az cap and for other it is minus az cap. We need to determine the magnitude. To determine the magnitude, we know that its dimension height is dz. Its height is dz and this point is at the center. So the magnitude of this is dz by 2. So this vector would be dz by 2 az cap. This vector would be minus dz by 2 dz. So to reaching the top surface, we need to displace dz by 2 along az cap. So the new point where we reach is xc, yc, they do not change because the displacement is only along z direction. Zc plus dz by 2, because it is very obvious, if you move upward, the value of z will increase. By how much did it increase? It increased by half of the height. Now, from this logic, what is the center of the bottom surface? It is very obvious that the x and y do not change. The only displacement is along z. If we go downward, the value of z decrease. By how much did it decrease? It decreased by dz by 2. So the center of the bottom surface is xc, yc, zc minus dz by 2. Similarly, if I go to the right surface, from the center of the right surface would be at, see this, to reach the right surface, you are moving along the x direction. To reach the left surface, you are moving along minus x. That means in this direction, x value would increase. In this direction, x value would decrease. So the center for the right surface would be xc plus dx by 2, yc and zc. See that there are no changes in y and z. Whereas the center for the left surface would be xc minus dx by 2, yc, comma z. Very obvious, nothing new. Similarly, I can do that for front surface and back surface. I would give you the result. I would ask you to try that at your home. At the top surface and bottom surface, the centers are xc, yc, zc plus dz by 2, xc, yc, zc minus dz by 2. Similarly, for the left and right, the change only in x direction. For front and back, the change only in the y direction. So now we have centers of the surfaces, we have normals to the surfaces, we need the range of variables. Again, let us consider the top surface only. The center is at xc, yc, zc plus dz by 2, but see, this is a plane parallel to xy plane, so here z is equals to constant. So once I know the value of z is going to be constant at zc plus dz by 2 wherever I move on the surface. That means at the top surface, the value of z is fixed. What about the values of x and y? The values of x and y are changing. Obviously, they should change, otherwise you cannot form a surface. A surface can be formed with a change in minimum of two variables. So the change is in x and y. Now, the center of the change is xc, but what is the lowest possible x value and what is the highest possible x value for the given surface? Similarly, if you are at here, what is the lowest possible y value and what is the highest possible y value at the top? Now, to understand that, let us look at the dimensions of this cube, the cuboid. The dimension is px and the center midpoint is xc. Then obviously one end point is xc minus dx by 2 and the other end point is xc plus dx by 2. Now let us look at the y dimensions. The dimensions along y is dy. And the center is at yc. Then again, the limits are from yc minus dy by 2 to yc plus. Again, for the bottom surface, if you consider the bottom surface, I have already told you bottom surface is just parallel to top surface. So the range of variables are same except the value of z. The value of z is constant, but it is not zc plus dz by 2. Instead, it is zc minus dz by 2. And its normal is, as you know, minus az cap. Its normal is along az cap. Right there? Now, I'll give you the answer for range of variables. I urge you to try them on your own. Again, for top, left and right surfaces, the values of x are constant. At the left surface, the value of x is constant at xc minus dx by 2. There is change in y, yc minus dy by 2 and to yc plus dy. Similarly, the change in z is from zc minus dz by 2 to zc plus dz by 2. So is the case for right surface. In right surface, y and z are changing, but the value of x is constant at xc plus dx by 2. Similar is the case with front surface. In front surface and back surface, the values of y are constant, but the values of x are changing. Now, to determine the expression of divergence of a vector field, we need a third part, that is the values of vector field at the particular surfaces. To understand that, let us dive deep into these vector fields. A vector field can be expressed as sum of three mutually orthogonal vector fields, where this is vector field 1, this is vector field 2, and this is vector field 3. Vector field 1, 2, and 3. How did this vector field form? This vector field formed with help of a scalar field. Scalar field 1, scalar field 2, and scalar field 3. I hope you get where I am going. If you have seen the gradient of the scalar field, I think you know where I will be going. So the vector field V bar is comprising of three components which are orthogonal to each other. This, and this. Out of them, you see in every term, the first term, which is scalar field, would be varying with space, whereas Ax cap is not varying with space. Similarly, Vy term is varying with space, whereas Ay cap is not varying with space. Similarly, Vz is varying with time, space, whereas Az cap is not varying with space. You may look at the concepts of unit vectors if you have to understand why Ax cap, Ay cap, and Az cap are not changing with space, because they are called universal unit vectors. Now, what will be the change in a vector field? Let the value of vector field at the center be Vc bar. So it would again have three components. The value of scalar field Vx at center, the value of scalar field Vy at center, and the value of scalar field Vz at the center, and in the directions of Ax cap, Ay cap, and Az cap respectively. Imagine that from center you have displaced a dl bar, where dl bar equals to dx bar dx Ax cap plus dy Ay cap plus dz Az cap. This would be the value of dl bar. How did we get there? You look at the differential length element. This is the differential length possible in a Cartesian coordinate system. Right? This is very easy. Now, because of displacement at the position, because it is vector field, there would be change in the vector field. Let the change in vector field be called dv bar. See, if I apply the principles of calculus to this expression and I write dvc bar, you know, d of a plus b plus c can be written as dA plus dB plus dC. So let me write this as d of this plus d of this plus d of this. But you know very well that Ax cap is constant. So this would be simply turning it to dvxc Ax cap plus dvyc Ay cap plus dvzc Az cap. Or even the centers can be removed. So the new value would be, of course, the original value plus the change. This would be the expression for change in the vector field. You identify this. dvx is nothing but change in the scalar field. dy is nothing but change in the scalar field. And dz is also nothing but change in the scalar field. Change in the scalar field can be represented as z bar dot dl bar, where z bar is the gradient, or let me say the differential operator. I would expand this term here, as we have seen in the earlier topics, that is gradient of the scalar field. dvx can be written as change in the scalar field because of x plus change in the scalar field because of y plus change in the scalar field because of z. Let me remind you what I discussed in the previous module. The changes in x, y and z are independent to each other. Because they are independent to each other, the changes because of x, changes because of y and changes because of z are also independent to each other. Now, changes because of x can be equated to rate of change along x times change in x. In that, this represents the change in x and this represents the rate of change in x. Again, this represents the change in y and this represents the rate of change in y. This represents the change in z and this represents the rate of change in z. And this total expression is the change in scalar field, where the first term corresponds to the change in scalar field because of x, the second term corresponds to the change in scalar field because of y, third term corresponds to change in scalar field because of z. Not just that, I can expand this dvy also in the same form, dvz also in the same form. Now imagine a scenario where there is no displacement along dy and dz. There is only displacement along dx. Then what would be dv bar? Then dv bar would be directly dou vx by dou x dx plus dou vy by dou x dx. This is along Ax cap, this is along Ay cap, plus dou vz by dou x dx along. This is the change in the vector field if there is displacement only in x. Whereas this, if there is displacement in x, y and z. If there is no change, simply in this expression substitute 0. When in the variable where there is no change, the expressions would give you the. Now that we have understood how the vector field would change, let us go back to the surface integrals concept and try to integrate this. So this is the expression of the change in the vector field as total. As I told you, if there is change in no other variable, I can directly substitute those non-changing variables to 0. Now let us go back to the vector field on the top surface. The vector field on the top surface, to reach top surface from center, we have displaced only along z direction, and the displacement is dz by 2. The magnitude of the displacement dz by 2 and along the direction of az cap. Now because of that, the change would be like this. You may look in the previous expression and there put dx equals to 0, that means dx equals to 0, dy equals to 0 and dz equals to 1 by 2 times dz. If you substitute these values in the previous expression, it will be. So this is the change in the vector field if we are moving from center to the top. So what is the value of vector field at the top? The value of vector field at top is equal to this, adding of the components. I hope it is easy to follow. Right? Now, let us look at the value of vector field on bottom surface. So, to reach bottom surface, you have traveled minus dz by 2. That is change in negative z direction. Here, the values of the displacements are dx equals to 0, dy equals to 0, whereas dz equals to minus dz by 2. So if you substitute those values, the answer you will be getting is this. Negative sign indicates decrease in z. Now, what is the value of vector field at the bottom surface? The value of vector field at the bottom surface is the change plus the original value, that is this. Similarly, you can also calculate the vector field on the right surface because the displacement is along a. Here again, dx equals to 1 by 2 dx, dy equals to 0, dz is equal to 0. If I substitute those equations, I will be getting. Now again, this is change. So the vector field on the right surface is equals to Vc bar plus Vb bar. The answer would be. If I talk about the vector field on the left surface, the entire thing would be same, but the value of dx is minus dx by 2. The value of dy is still 0. The value of dz is again 0. There is no change in y and z to reach the left surface. This is the change, and the value of the vector field at the bottom surface, at the left surface is. Now, at the back surface, again, the only is dx changes, dx equals to 0, dy equals to half dy, and dz equals to 0. value of vector field at the back surface is now. And the front surface, again, there is no change in dx. Dx equals to 0, dy equals to minus 1 by 2 dy, and dz is also equals to 0 to reach the front surface. So the value of vector field at the center of the front surface is. So in the requirements which I have given, I have considered cuboid, I have determined the volume of the cuboid, I have the expressions for differential surface elements for all surfaces, I have also analyzed the limits, I have also obtained the values of the vector field at the different surfaces. So I have all the required quantities to determine the divergence. So now let us look back. The divergence of the closed divergence of the vector field is this closed surface integral divided by volume. Now, so let me first determine the closed surface integral. This closed surface integral is the sum of 6 different open surface integrals. Let us calculate the integrals one at a time. If I see the bottom surface, this is the value of the vector field at the bottom surface, and this is the differential element at the bottom surface. Now, using the principles of dot product, this would be vanishing because ax bar dot az bar equals to 0. This would be vanishing because ay bar dot az bar equals to 0. Only this term would be remaining. So I should be integrating this over vzc minus 1 by 2 dou vz by dou z times dz, and integrated over the limits of n. Now, what are the limits? I also know the limits. The limits are xc minus dx by 2 to xc plus dx by 2, yc minus dy by 2 to yc plus dy by 2. Let me erase for since these are the limits. Now, if I first integrate over y, over the limits of yc minus dy by 2, integration of dy is y. When I substitute the limits, I would be getting, when I substitute the limits, it is very simple that I would be getting dy, because if I subtract yc plus dy by 2 minus yc minus dy by 2, yc would be cancelled out, dy by 2 minus of minus dy by 2 would give me plus dy by 2 plus dy by 2, this is. So here it is, dy is remaining. Now, if I integrate dx, the answer would be x, and the limits are xc plus dx by 2 and xc minus dx by 2. Again, if I subtract this, I will be getting dx. So the answer is minus vzc dx dy plus 1 by 2 times dou vz by dou z dx dy and dz. If I consider the top surface, the value of the top surface vector field at the top surface is this times this is the differential surface element for the top surface. Again, this would be vanishing, this would be vanishing, only this would be remaining, and if I integrate them, the answer I would be getting is. If I calculate the left surface, this is the value of the vector field at the left surface. Again, this would be remaining, this would be vanishing, this would be vanishing. The answer I would be getting is vxc dz dy minus vxc dz dy plus 1 by 2 dou vx by dou x dx dy. If I calculate for the right surface, again, these would be remaining, these would be vanishing. The answer would be. If I calculate for the front surface, again, these would be vanishing, these would be remaining, but these would be vanishing, these would be remaining because it is ay. So the answer would be minus vyc dz dy plus 1 by 2 dou v by dou y dx dy. If I calculate for the back surface, this is the value of the vector field at the back surface. when I dot with this, these would be vanishing, these would be remaining, these would be vanishing. The answer would be, so please make a correction that it is dx, dz also, right? They are missing here. So when I calculate the closed surface integral, the answer would be this. These are the 6 different surface elements and they are being added. If I look into this, I can say that these two cancel each other, these two cancel each other, these two. So these would be, the answer would be, this is net outward flow from a given body. Right, given surface, that is closed surface. Sometimes I can also call it as given. Now, what is divergence? Divergence is the net outward flow per unit volume. So I should be dividing that by the volume of the body. The volume of the body is dx d by dz. So when I divide that, the answer I will get. This is the expression for divergence of a vector field on Cartesian coordinate system. You may use this knowledge and determine the expression for divergence of vector field in cylindrical and spherical coordinate system. The important change you should be noticing is the values of unit vectors are not constant. They will be changing with space. This is the reference material which you can find elements of electromagnetics by Match Study. Thank you. We'll meet in the next module.